Alright, we are starting today by looking at rational functions, and we're just going to do a big overview on rational functions. There's something that you studied in a second year algebra class, and we're just going to review some topics today that are going to lead us to the majority of Unit 9, which will be limits and dealing with asymptotes. So today we're going to focus on simplifying rational expressions and finding the domain, range, and zeros of rational functions. So first thing, a rational expression is written in the form numerator over denominator. So if you think about the word rational, it has the word ratio in it. Ratio can be written as a fraction, so we're going to have some function in the numerator over a function in the denominator. A rational equation then is when you have your numerator over your denominator set equal to another variable. So in this case we're looking at f of x equals numerator over denominator. If you remember from previous units, it's very important that we simplify our expressions, but we solve our equations. Alright, so simplify the expression. We're not setting this equal to 0. We are not solving for a final answer. We're just going to do some algebra to try to simplify as much as possible. So in simplifying expressions, you want to think about finding your GCF and canceling things out. So in the denominator, both of these things have an x. We can factor that out. We're left with y plus 1. And on the top, we just have 3xy. But an x in the numerator will cancel with an x in the denominator. And our simplified expression will just be 3y over y plus 1. Remember, you cannot cancel a y here and here because your denominator has addition in it. Alright, next one. Greatest common factor in the numerator. Looks like it's going to be an x. If I take out an x, I'm going to be left with x squared plus 5x plus 6 all over. The bottom is going to factor into a difference of squares, x plus 2, x minus 2. Nothing cancels yet, but if we think about that numerator, this trinomial will factor again. We're going to have x plus 3 and x plus 2, things that multiplied to 6 and added to 5, over x plus 2, x minus 2. We can cancel out an x plus 2 in the numerator and the denominator. So our final answer will be x times x plus 3 all over x minus 2. Alright, continuing on. This next one is going to have some factoring in it, and then we're multiplying. And remember, when you multiply fractions, you just multiply straight across, so there's nothing to do here as far as rewriting other than to consider our factoring. So this purple one is going to factor into t minus 3, t plus 2. This one's going to stay just as it is. Can't factor that anymore. This one right here is going to result in t plus 3 times t plus 3. And this last one is again a difference of squares, just like the previous example. T minus 2, t plus 2. Now, since all of this is being multiplied, we can cancel things in the numerator and the denominator. So I've got a t plus 2 in the numerator, cancels with one in the denominator. T plus 3 will cancel with one of these. So my final answer is looking like t minus 3 over t plus 3 times t minus 2. And again, you could FOIL those together on the bottom, but for right now we're trying to simplify to help us eventually look at domains and also consider asymptotes. So I'm going to leave it in its factored form for a final answer after it's been simplified. Alright, last one. This numerator is going to be a difference of squares. We're looking at x plus 5 and x minus 5 over 5 minus x. Now, it looks like something should be able to cancel, but we've got to do a little bit of work on this denominator to get us there. So if I take out a negative 1 out of this 5 minus x, I'm going to be left with negative 5 plus x. And that's going to get me my positive x value, which is helping cancel with one of those. Now I'm going to rewrite that as negative 1 times x minus 5. You can check by distributing. If I put this back in, I get a negative x and a positive 5, so I'm okay there, which means that I can rewrite this function as x plus 5 x minus 5 all over negative 1 times x minus 5. Now these x minus 5s will cancel out, and I'm left with x plus 5 over negative 1, which is the same thing as negative x minus 5. Okay, so this skill of pulling out a negative 1 to help something cancel is very important later on when we're looking at limits. Okay, so in previous units we have studied domains. Domain is the input values or the independent variable, the x values. It's what are all of the numbers that you can put into a function that will lead you to getting an output value or your range of values. The range is dependent on the domain. So again, what did you put in? Domain to get out your range. Looking at these two functions, your domain of your function, if you think about it in pieces, plugging in x and taking away 3 is fine. There's no problems with doing that. But as soon as you put x minus 3 in the denominator of a function, we do have a problem in mathematics with dividing by 0. So our domain value is going to be that x minus 3 can't be equal to 0, which means that x can't be equal to 3. So our domain is going to be all reals with x not equal to 3. If you remember from notation, you can write that as negative infinity, comma, 3 in union with 3 to infinity. I would accept either one of these for a final answer. The domain of this second one, it's kind of hard to tell. This bottom function on its own is perfectly okay, right? We can square a number, subtract 5 times the number, and subtract 14. The numerator on its own, you can square a number and multiply it by 6. But when you put these together into a rational function, we have a problem because we cannot divide by 0. So our first goal is going to be to figure out what is making us divide by 0 here. And if I start to factor this, simplify it just like I did on the previous examples, nothing's going to cancel out, and we have problem spots when x is equal to 7 and x is equal to negative 2. So our domain is going to be all real numbers with x not equal to 7 and x not equal to negative 2. If you want to write that in interval notation, it would look like that. Now, thinking about our range, we are going to want to take out our graphing calculators and look at the picture of these functions, because we often look from bottom to top to help us figure out the range. Well, with rational functions, ranges can be a little bit tricky to figure out because you do cross over some horizontal asymptotes and other things happening. So for today's lesson, we're going to focus on domain. I would like for you to consider the fact that you can find ranges by looking at the graphs, but we are not going to spend time looking at the range of rational functions today. We are going to work on finding zeros. So if you remember, a 0 is the input value that results in an output of 0. So what is your domain value that results in a range value of 0? So we're looking for an x value that makes y equal to 0, in which case we want to first start by setting our y's equal to 0. Well, if you remember, g of x or f of x or m of x represents the same thing as y. It's your output. So I'm going to replace that with a 0, and I'm going to solve for x. So the first thing is multiply both sides by x minus 3. Those are going to cancel, and I get x minus 3 times 0, which is going to result in 0 equal to 1. Is this ever true? Hopefully you answered no, in which case we know that there are no zeros to this function. The next one, same thing. I'm going to replace my y value, or my h of x, with 0, and set that equal to 6x squared over x squared minus 5x minus 14. First thing I'm going to want to do is multiply by x squared minus 5x minus 14 to try to clear out my denominator. Again, on the left side, this all turns to 0. This side we get 6x squared. Solving for x, I get that 0 is equal to x squared, which means that x is 0. So the 0 of this function, when I put in 0 for x, I will get back 0 for y. Or you can just say when x is equal to 0. Okay, so again, domain, think about what makes the denominator 0, because that's going to make things undefined. Finding the zeros, you want to set your y value equal to 0 and solve for x. So here is a function, f of x equals 1 over x minus 2, and I have the graph sitting next to us. Looking at your domain, if we do things analytically, we should see that it's this denominator that's causing us a problem. So our domain is going to be all reals with x not equal to 2. If we translate this domain over to the graph, look at what's happening at x equals 2. We have a vertical asymptote. Vertical asymptote at x equals 2. That's based off of our domain. Looking at our range value, I said we weren't going to focus on this a lot, and we're not going to, just only in the basic examples, such as this one. Looking from the bottom to the top, we go from negative infinity, getting really close to 0, and then we pick up on 0 and keep going and keep increasing until infinity. So our range here is going to be all real numbers with y not equal to 0. If you notice, there is a horizontal asymptote at 0 based off of our range value. Now again, what we're going to encounter is that horizontal asymptotes are really only holding their position as you get out to negative infinity and infinity. Some rational functions will have horizontal asymptotes, but they'll be able to cross them in the middle. A vertical asymptote, though, is like a brick wall. You may not cross a vertical asymptote ever. Horizontal asymptotes, though, are going to have some of their own features that we will look at in some later videos. So again, simplifying rational expressions, go ahead and cancel things out just like you did in second year algebra. Solving rational equations when you're looking for zeros, go ahead and set your y value equal to 0 and solve for x.